Okay, hello everyone. Um, I think we have practiced some uh, examples from improper integral. Okay, and uh, there's one section in the improper integral that I need to talk to you today. So it's about the comparison theorem. Okay? The comparison theorem. Okay, well the text still waiting for appearing. Let me give you some introductions. So basically, what we are going to discuss today is, firstly, it's called the comparison theorem. Okay, so if you have the functions f, g, all functions continue, and for x greater than some constant a, if you have the integrations a to infinity of the functions f, okay, fx dx, if this is convergent, okay, then the integrations of g with the same integration also convergent. Okay, so back to the comparison theorem. Okay, so yeah, so based on this the comparison, what you can do with this theorem is, if you have any integrations and you don't really need to worry about, let's say you have integrations, maybe 1 infinity, and you have some fx here. Okay, if it is only asking, okay, if it's only asking, if it is only asking, it's converges or diverge, without necessarily, if converge, you need to assign value. Without knowing the value, we can use the comparison. We can use the comparison. So we can, or comparison theorem can be used, okay, to determine whether it's converge or diverge. Okay. Now, how to use the comparison theorem? Okay. The first thing is to set up other functions aside from f. Okay. Let me just use um, let me use age. Okay. So we can separate this fg and this age. Okay. So let me use age here. If I have 2x, okay, another function, and I can integrate this ux, okay, that's ux, dx, and integrate, okay. For example, if this ux is greater than the hx, if, and if this is convergent, if this is convergent, then based on the first theorem here, if the f is greater than g, and if f is convergent, the g also convergent. Okay. So what we need to do is we need to set up this u. Okay. It can be any functions that you can think of. Okay. But probably the easiest one, like we deal the other day, on last week, we deal with the and depends on p. It can be converged, it can be diverged, right? And we can use any simple functions like this one, and then compare with the questions. If we can prove this is true, if this is true, then the questions h, x, dx also converge. And we can add by the comparison theorem. Okay. Let me give you the example. Okay. Now, the question is only asking, is this integrations converge or diverge? So you don't necessarily need to compute this and maybe find the value. But you can use the comparison theorem to prove that, okay, maybe this is converge or maybe diverge. Okay. Or maybe I will change it, maybe not 0. Okay, maybe not 0. Maybe first deal with 1 first. Okay, we deal 1 first. Because 0 will be another another problem, but later. Maybe 1 to infinity of x over x cubed plus 1 dx. Okay. Now, to use the comparison theorem, we need to establish the new functions, okay, based on our rational polynomials, right? Okay, let's see this x over x cubed. Okay, let's observe or consider do you know why I guessed this 1 over x squared? You see x and x cubed. Imagine it's only x and x cubed without 1. Okay, it's 1 over x squared. And from here, we can say that this is converged, right? We can say this is converged. And we need to prove at least we need to prove this. We need to prove this. So if you see the form here, it's always greater than the x cubed, this left part, because of plus 1. Okay, so this is true. So because this is greater than this, and this integration is converged, then this integrations from 1 to infinity also converge. Okay, this function is our setup. You can set this with any functions you want. Any functions. Any functions you want. And then set up the inequality, prove that, and if it's true, then it's also true that it's converged. Okay. So we can write here, so this converge by comparison theorem. So you are setting up the new functions that you can maybe prove whether that is greater or less. Okay, depends. Okay, let's go to the next example. Is the integrations and our next example. Okay, now see these questions. Do you have integration from 1 to infinity? You have 1 plus sine squared and over square root of x. Okay. Now we can observe Okay, you can observe. So this is converge or diverge? One over square root of x, converge or diverge? Diverge, right? Diverge, okay? So let's say this is diverge. And we can also say, remember that if you have this, if p less than 1, it will be diverge, okay? Now we can also set up the 1 plus sine squared x over squared x, and then let's say the sine, the maximum value is just 1. So this is actually greater than this, right? Okay, right? So this diverge because comparison theorem, or by, let's say by. Okay, how about this? Or maybe the complete question, sorry. Yeah, the question is only asking, is this is diverge or converge? Not necessarily need to compute the value, okay? So if any improper integral, if you have seen the questions and it is only asking only diverge, converge, you can go to comparison theorem. But before you go to comparison theorem, we need to know your other functions, okay? So we need to think other functions, but the easiest one is just 1 over square root of x, right? The easiest one is just this. And we need to find this first. Okay. So we need to set up the integration for the 1 over square root of x and find how this is convergent or divergent. And if we find this, then we can get proof from the sine squared, and we need to try whether it's correct or no. So we can set up the limit as t approaching 0 from the right side. So it's converged. Seems it's converged at, so it's converged. And we have the functions. At least this is, or this, both are correct, right? At least they may seem equal. So we can also say the is converged by comparison theorem. Okay. Okay. Any questions? Any questions? So um, so for this Friday, because it's holiday, we will skip the TA, right, for this week. So next week will be the last, I think, for our course also. So we still have, this Thursday will be the quiz. Next Tuesday, Thursday is basically our course. And I will finish off the chapter 8. I think I can start chapter 8 today, just a few, just a short introduction. And we can practice some parts on Tuesday and go for another part in chapter 8. And maybe if all is going smoothly, then Thursday we can review for final exam preparations. And Friday, next 2 weeks will be your last day, and maybe also final review for practice and exercise. Okay. I think I've announced the final exam schedule, right? Okay, on the Moodle. So in the building or the classroom is EE406. Okay. Start from 3:20, January 15th. Okay, if there's no questions, let me go to the arc length, the chapter 8, a little bit. Okay, short introduction. So if you are looking at your textbook, the textbook is, we will focus on 8.1 and 8.2, only two sections, okay? And then finish. Okay. So 8.3, 8.4, we will not discuss this semester. So chapter 8, we will start from the arc length. So do you know arc, the meaning of arc? Yes, yes. Like when you have a bow and arrow, the curve is called arc. Okay? So we need to find the length of the arc. Okay? So if it's asking arc length, meaning if you have a bow, you pull out the strings and it will make the arc, right? And arc length means the length of that arc. Okay? Or in our case, if we have functions, okay, let's say that's our functions. Okay, I'm just drawing randomly. Okay, so the idea of arc length is we need to, for example, okay, if we have A and until B here, okay, maybe the function is still continuous here or there, but we are only focused on A to B is equal, okay, A, B, and equal. So we need to measure the length, okay? Like when you have like maybe if you pull out, it will be like a rope, right? And you need to measure that, okay? But how to measure this, okay? So the idea, okay, I will give you um, some short introduction from the textbook, and then see if you understand those methods. And I will give you another method that you can choose which way you prefer, okay? So let's separate some points, okay, from this particular curve. Let's say we have point here. Let's say P0 or P naught, P1, and then maybe P2, and maybe some point here, maybe around here. And I will make the pattern for I. Okay, I minus 1, and then Pi. And then this part will be the Pn. Or to make it smooth, let's say the Pn will be the last part. Okay. Let's say this is our segment. Okay. So we can have P0, P1, one segment, P1, P2, and this point all become uh, a segment. Okay. And to make smoothly, let me erase this and give a little straight, because what I want to make now is a straight line. So from P0 to P1, straight line, and straight line. Okay. Let's say this is at the x1, and this is x2, and we have this x I minus 1. This is xi. Okay. So if this is the curve of y of f of x, okay, let me name this curve y of y is f of x. Okay. Let's define, okay, define the length, okay, length of curve y equal f of x, and from A to B, let's say L is length. Okay. So, okay, I hope you get the idea about the straight line. Okay, what the meaning, why we need to cut this whole curve with the point by point. Okay. Let me explain a little bit here. Okay. It's similar to integral, but what we need to plus is the segment. Okay. So if we make a short segment, we can plus all this, right? So the smaller the gap will be, it will be smooth, right? It will be correct to our curve. It will be similar, and maybe it will be the same. So the definition will be the same as integrations. So we will have limit, okay, Sn approaching infinity of our distance, okay, the segment distance. I will write the segment as pi minus 1 and pi. This is the distance, okay, the distance from pi minus 1 until pi. So distance. And then I will define also the delta y, okay, based on our curve and our notations. Let this be y, the difference between y I and y I minus 1. Okay. So let's write the distance. So the distance formula will be x I minus x I minus 1 and then squared. And then plus dy. Okay, now we can write this as delta x squared plus delta yi squared. Okay. This is the distance. Okay, let me move to the next slide. Or let me write this as the first. And let me also write the um, okay. Anyone notice this? This is actually this is the delta y, right? This is the delta x, right? This is the mean value term. Okay. Okay. From the same notations, I can make out the theorem for the mean value term. Okay. And I can write the fx minus fx I minus 1 becomes the delta. So this will be the delta. Okay. Now we have from previous uh, formula, we got the delta x squared plus delta yi squared. Okay, and let's substitute with this one. Substitute these two to the first formula. Okay. Now I have delta x squared and delta x squared also in this side. I will remove the delta x, go outside. So let me write this as 1 plus squared and then delta x. Now we have L is limit as an approach infinity. And we got this expressions, okay? 1 plus f prime and then squared, and then delta x. Now from this limit and the sigma, we can relate this relation to the integral, okay? The integral. So if we observe the interval a to b, okay? So we can write this as that's the formal definitions that we can look up to. But I will show you another way to look at the curve and how to establish the formula. Okay. This is in the textbook. If you look at the textbook, this definition is similar to textbook. But I'm not suggesting to go here. With some technical words, we will have some difficulty to sometimes to understand why this is happening. Okay? Let me give you another one. Maybe this will help you to understand. Okay. Okay. Let me give you some another approach to see the arc length. Okay. Okay. Now focus on this blue line, the curve. Okay. And let's say we have a tangent line. Okay. Okay. Let's see if this is helpful for you. Okay, imagine you have a tangent line here. Okay, and if you are making a straight line like that, and we can also make a triangle. Okay, and we can see that this is dx, this is dy. Okay, and let's say we have dl here. And based on just Pythagorean formula, okay, I can write dl. Okay. Now I can also write and try to rewrite the form. So first is dx squared still. Now I can write this as okay. I can write this right, same. Okay. So dx squared, and then dy squared. I will write dx squared and then dy over dx squared. Okay. I will factorize this dx going outside of the square root. Let me write in blue. So dl will be 1 plus okay. So if I'm giving the integral, okay, I will have L is integral let's say from A to B. Okay. and you get the same arc length. Okay, this is by geometry. Okay, by geometry, if you see the curve by geometry, and you already know the differentials. Okay, this D is differentials. You already know. You already learned, and we can also write this. Okay, but okay, if you are not really not sure about the differentials and maybe haven't learned about it, this seems weird, okay? Because you define and then p, but I think because we already learned in the first half of our calculus, we already learned that dx or dy will be, it's called also the differentials. Then this is, you can uh, derive the formula. If you just look at the triangle at the curve, okay? So just look at the triangle, define dl, and this will be your arc length, okay? Like if you have dl, and then this is also dl, in other part we have a dl, and then you plus all the tangent line, right? So all the tangent line will be added from A to B, for example, and then that's the arc length. Okay, any questions? No? Maybe I can give you some examples. All the chapter 5, 6, 7. Okay. Okay, maybe first is integral. Okay, anyone solve this one? And then the next questions, evaluate. So it's the final exam is chapter 5 to 8, but actually it will cover most of all chapters. So let's say we have this limit, okay? And this the second question. And how about the first question? Anyone solve? If you can solve the first one, can you raise your hand? Mhm. No, I think you cannot solve with this. Yeah, you use other techniques. Bisa. Tapi apa yang disubstitusi? Pakai apa? Paling nggak harus beda satu kan? Itu kan sama-sama kuadrat kan? Wait. Uh, I think no. Yeah, continue, continue. Yes, 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 yes. You get it? Okay. You can, yeah, you can continue that. That. Mm. Yeah, continue, continue. We're on the right track, right path. Yeah, use sign or cos. Yeah, use sign or cos to substitute. Yeah, it will be the same, sign or cos. Yeah. Here. Okay. This. Okay. Okay. My answer for number 1 is 5/12 minus square root of 3/8. I think you are missing the half. Yeah. For number 1, 5/12. So I think you have half in the front. Do you want to solve? Do you solve this? Okay. I think too long. Let me continue at the board. Oh, let me just continue here. Okay. This is maybe just my suggestion for some strategic approach. Okay, how you deal with any integrations, which techniques you should use, and how to solve. Okay. Now see this square at the top. This is also squared. Of course, any general substitution will not work. Like the u sub is not working because you sub you need to use at least the difference should be at least 1 degree. Okay, for any polynomials. Okay, and then the next techniques that you can think is maybe integration by parts. But if you are having like, oh, maybe we separate this, become this and this. Okay. And this will make your life difficult, right? And don't do this. Don't, don't do this. Now, see this form, okay? And remember that whenever you have like 1 plus x squared, 1 minus x squared, and then maybe, yeah, at least you have these two possibility. You can think from the trigonometric approach, you can have this. You can say that this is at least this form is similar to this squared, right? So you can use, or you can choose x as sine or cosine. Okay, let me just write sine. Okay, because if I'm writing x is maybe sine theta, my dx will be just cos theta d theta, right? And if you plug in this 1 minus cos squared here, it will be sine squared, right? Sine squared, you square root becomes sine. Okay, so this become. Let me just write this first, and the sine squared theta, and write it along, and then cos theta d theta, and then sine theta, right? Or cos, sorry, should be cos, right? 1 minus sine is cos theta. And you can have this. So you have this sine squared theta d theta, but you need to see this first. So when you x 0, sine, what sine should be 0 is 0, right? And it's half, it's 5/6, right? Okay. Or if you're confused, you can look at the theta is tangent inverse x, okay? Or arctangent x, and then you can choose any number that can be possible for this case, okay? Now sine squared theta, if you encounter just sine squared or cos squared, the easy way up for me, you can use the identity cos squared theta minus sine squared theta. Okay, and you can have at least two forms. The first form is 2 cos sine squared theta minus 1, and then the other one is 1 minus 2 sine squared theta. Okay. Now we have sine squared, so the second form, right? So we can write the sine squared theta is equal, right? Now we can write all the terms, or let me write half, and then I will write 0, 5/6, 1 minus cos 2 theta. So this will be half, and then theta, and then minus sine 2 theta over 2 from 0 to 5/6. So 5/12, and 5/6 2 is 5/3. Sine 5/3 is what? Is half square root of 3, 4, 2, 2, 2, and 4 become 8, right? So it will be 3, 8. Okay. Yeah, the same, right? Okay, number 2.